The world's first great flyers were not birds. They took to the skies 60 million years before the first known bird. And then they vanished, leaving scant clues about how they lived. These were the pterosaurs, also known as the pterodactyls. These flying reptiles were cousins of the dinosaurs. 65 million years after the last pterosaur disappeared, scientists ask, how did reptiles learn to fly? On the shores of the Niobrara Sea, 85 million years ago, a young pterosaur stretches its wings for its first flight. With a wingspan of nearly 20 feet, it scans for its first prey beneath the blue waters. In the still waters of the Niobrara Sea, carcasses drifted to the bottom and were fossilized, undisturbed by currents. Today, all that remains of the Niobrara Sea is a dusty limestone chalk bed that runs from North Dakota to New Mexico. It is one of the few places in America where the fossils of pterodactyls are found. Like the dinosaurs, pterodactyls were reptiles, more akin to lizards than birds. Yet, like birds, pterodactyls could fly. Among the last of these flying reptiles was Pteranodon. Paleontologist Chris Bennett has spent thousands of hours prospecting for pterosaur fossils in the Niobrara chalk beds in western Kansas.
85 million years ago, this would have been at the bottom of a sea. It would be about 200 meters deep, and it ran from the Arctic Ocean down to the Gulf of Mexico, and the near shore was about 200 kilometers from here. The sea would be full of large mosasaurs, seagoing lizards, turtles, plesiosaurs, all sorts of fish, and above would be flying Pteranodon. A typical day in the life of Pteranodon would be flying out over this Niobrara Seaway, soaring on the wind, flapping occasionally in order to gain altitude and so forth, but mostly soaring on the wind, just as a lot of modern seabirds and large birds do today. They'd be chasing after schools of fish to feed, and probably would be spending most of their time feeding. At night, they probably would just rest on the surface of the sea as living albatrosses do today.
Over the past 125 years, 1,100 fossils of Pteranodon have been unearthed here. In the autumn of 1870, the area was explored by eminent Yale paleontologist O.C. Marsh and his Wild West-style hunting party, toting guns and Bowie knives. In the pioneer days of paleontology, the photos made good souvenirs to send to the folks back east. So, too, did the fossils of Pteranodon. Marsh's discovery of Pteranodon opened a new chapter in the history of pterosaurs. Pterosaurs were not dinosaurs. As far as paleontologists can determine, pterosaurs descended from small, lightweight, four-legged reptiles that lived about 250 million years ago. By 225 million years ago, the pterosaurs were accomplished flyers. The pterosaurs came in two evolutionary waves. The first of them were called ramphorhynchoids, meaning pointy, curved nose. Their fossils reveal they were only about the size of pigeons. The ramphorhynchoids had long, skinny heads filled with teeth probably used for plucking fish out of the water. These early pterosaurs had long, stabilizing tails, like the tail on a kite. Their definitive evolutionary feature was a super pinky. The fourth finger on each hand had become longer than their entire bodies and supported a wing. The other fingers, normal-sized, developed claws. The first rhamphorhynchoids date back more than 200 million years. By 150 million years ago, they had evolved in great variety and covered the globe. The fossil record of the rhamphorhynchoids spans almost 50 million years, from 230 to 180 million years ago. For unknown reasons, by 180 million years ago, the rhamphorhynchoids vanished. A second stage of pterosaur, the pterodactyloids, rushed in to fill the gap. They exploded into a strange and diverse group. The earliest were the size of robins, but over millions of years, some grew as large as a twin-engine plane, with a wingspan of almost 40 feet. They weighed from a few ounces to 200 pounds. Most lost their teeth, though some developed rows of bristles, perhaps for filtering food from the water. The newer model pterodactyloids shared longer heads crowned with magnificent crests that could be up to twice the size of their bodies. Their head bones had become very lightweight, and their necks became bird-like, flexible, and strong. Their tails shrunk to little stumps, no longer useful for flight. The loss of the long tail heralds an important change for the flying reptiles. Without it, they depended more on subtle wing adjustments to compensate for changes in air currents during flight, behavior that implies greater intelligence than the earlier rhamphorhynchoids. Flying is perhaps the most strenuous evolutionary adaptation ever to arise. Scientists define two kinds of flying, soaring and flapping. Soaring flight, which depends on updrafts and breezes, requires less energy than active flapping. Like bats and birds, pterosaurs had skeletons which accommodated the large flight muscles controlling their oversized wings. Paleontologist Bob Bakker believes their muscular development indicates pterodactyls were strong flyers.
If you analyze pterodactyls in the front leg, in the back leg, in the torso, there's no animal that's ever evolved such a complete commitment to powered flight. Nearly every ounce of body muscle is tied to the flight muscles. These were exceptionally sophisticated, exceptionally strong flyers.
It takes enormous energy and muscle strength for all that flapping. That requires a sophisticated metabolism, a warm-blooded metabolism. It also takes a nimble and sophisticated brain. Scientists believe pterosaurs had both. Pterosaurs' commitment to flight was capped by a lightweight but very strong skeleton. Berkeley paleontologist Kevin Padian is an expert on the evolution of flight and the anatomy of pterosaurs.
First thing to know about pterosaur bones is that they have the thinnest bones of any vertebrates. This one's squashed completely flat, flat as a pancake. And it's like it was just like it was run over by an 18-wheeler sometime in the Cretaceous there in the middle of the ocean, right? And this bone comes from the upper arm like this. It's squashed completely flat. The bone wall is so thin, it's about the same dimension as the wall of a dirter. A dirter is one of those things you get at the end of the paper towels, the cardboard thing in the middle, you go dur, dur, dur in it. Well, that's what this thing is like, except there's nothing in the middle of it. I mean, it's just completely air-filled, and it's squashed flat, and the bone walls are very, very thin. Now, you might think this would make it a very weak bone, but in fact, we checked this out with some engineers at Stanford, and we're working with them, and they showed us that, in fact, the big diameter of this arm is what really makes it strong.
Despite its hollow center, the thickness of the walls of the pterosaur bones enabled them to withstand the forces of flight. Calculations show that pterosaur bones are up to 86% stronger than similar mammal bones. Scientists agree that even the enormous pterosaurs could fly. But how? 200 million years ago, a great sea covered this area in southern Germany. Animals living along its shore would fall in, die, and become buried by the fine, silty deposits. Over millions of years, these deposits would harden into a smooth limestone. For centuries, this limestone had been quarried to make tiles and artist stones. But in the late 1700s, something unusual was pulled from this quarry. A strange and twisted fossil with the body and head of a lizard. Its long, curving fingers were simply incomprehensible, almost dragon-like. It landed, as interesting fossils of the day often did, on the desk of Georges Cuvier, the brilliant French anatomist. If restored to life, he wrote, the fossil would resemble nothing in the modern world. In the early 1800s, a time that knew nothing of extinction, Cuvier's contention was revolutionary. It was the seed of an idea that would become a fundamental principle of evolutionary theory. Cuvier named the creature Pterodactylus, or wing finger. To him, it was clear that this extraordinarily elongated last finger bone had supported some kind of wing. Scientists tried to explain how a primitive reptile could ever retain the advanced powers of flight. The verdict was that they could fly, barely. Otherwise, they'd still be around. Paleontologist David Unwin of the University of Bristol, England, has studied the evolution of the pterosaurs.
For many, many years, people thought that it was really a poor kind of flyer. They thought these animals were only capable of hurling themselves from cliffs and crashing to the ground and then sort of staggering back up again and doing the whole thing over.
At the turn of the century, the English geologist H.G. Seeley wrote a popular book called Dragons of the Air. After studying pterodactyls for decades, Seeley argued they were extraordinarily sophisticated, warm-blooded flyers. His opinions did not prevent the pterodactyl's fall from grace. Science decided that the first experiment in non-insect flight was an abysmal failure.
Professor Seeley at Cambridge in the 1870s had a magnificent monograph about pterodactyl joints and how they moved, and he said these were hot-blooded like birds and powerful flyers, very agile and able critters. Then in the 1930s, the pendulum swung and people said they're not hot-blooded, they didn't have good joints, they had weak wings, and they just could barely soar in the air, and the least little turbulence would send them fluttering around like a poorly designed Air Force production.
The pterosaur's flight into obscurity would last almost 50 years. Then a generation of scientists raised on Hollywood's image of these creatures would take a fresh look at them. Pterosaurs went from evolutionary failures to pioneers of flight. It was the first time on Earth that an animal other than insects developed the ability to fly. The predecessors of these winged reptiles appear about the same time as early dinosaurs, 225 million years ago. Paul Sereno has found some of the earliest fossils ever discovered, pushing back the family tree for dinosaurs, and now, quite possibly, for pterosaurs.
And so we think that pterosaurs are not modified dinosaurs, but arose from a different kind of reptile nearly the same time. If you went up to the family tree of dinosaurs and took the whole tree off, pterosaurs would not be in your hand. They're outside that.
Scientists have nothing to compare the pterosaurs to. The only other backboned animals that can fly are birds and bats. Since the 19th century, paleontologists believe that pterosaur wings were bat-like, leathery, stretching between 4 elongated fingers and their feet. Bats' wings attach to their hind legs, making bats strong flyers, but presenting a burden once they've landed. On the ground, bats walk on 4 legs, awkwardly lifting their wings off the ground. David Unwin supports the bat-like view of pterosaurs.
And basically the hind limbs are sprawling out sideways and the feet are sort of turned right out like this, and then the forelimbs came down and they had 3 little fingers and claws on the ends down there, and they put these down on the ground, and they had the enormous great wing finger would be spreading up round and over the back, and they moved along rather slowly and very laboriously. Remember, they have wing membranes attached to their hind limbs and going between their hind limbs, so they move along quite slowly and laboriously, and they certainly didn't move very fast at all when they were on the ground.
Other scientists believe pterosaurs were 2-legged and bird-like, with narrow wings attached at the hips, leaving their hind legs unencumbered for walking. Paleontologist Kevin Padian demonstrates.
Pterosaurs walked like birds and the other dinosaurs. And the reason we know this is they have their pelvis and their hind limbs set up like the feet of dinosaurs and birds. They have thigh bones in which the head of the thigh, the femur, comes right into the socket like this, very much like our femora. Now, if you just look at our femora, which has this big ball and socket joint, we could stick our legs out like this and we could walk like that. But in fact, we don't do that. How do we know that? We look at the rest of the leg. And in pterosaurs and birds, they have this femur that goes out like this, and they have a knee joint here. They have very long shin bones. They have an ankle that only works like a hinge in this direction. So they have to walk pretty much like this, very much like birds do. And they also walked on their toes. So they put one foot in front of the other. They're slightly toed inwards, like birds, like dinosaurs.
The fossil record doesn't contain a perfectly preserved soft tissue imprint that could answer the question of bird-like or bat-like anatomy. Paleontologist Chris Bennett feels that comparisons to birds and bats will never sufficiently explain the remarkable fossils of the pterosaurs.
I think we could learn a lot about pterosaurs by comparing them to the living flying animals, birds and bats. But I also think that the pterosaurs are as different from birds as they are from bats, and probably as different from those two as birds and bats are different from each other. And I think basically pterosaurs are pterosaurs.
Though our picture of pterosaurs has changed with new evidence, their place in our imaginations has never wavered. Bob Baca has followed the pterosaur's trajectory through science and popular culture.
I like pterodactyls. A lot of people like pterodactyls. How science has viewed pterodactyls has gone in a complete circle. The most exciting thought about pterodactyls is this. You watch a movie with good pterodactyls. Watch King Kong. You know, the pteranodon that tried to eat Fay Ray, this great big black, harpyish, ugly pterodactyl comes down, grabs Fay Ray, and she screams, and King Kong saves her. What we're realizing now is something awfully obvious. Pterodactyls weren't gray. They weren't ugly, bat-like, black monsters.
While the question of wing structure remains unsettled, scientists look for other clues to pterosaur behavior. The answers may lie in the Niobrara chalk bed in Kansas, where the fossils tell a surprisingly detailed story about the lives of the pterosaurs. For decades, paleontologists recognized that two distinct types of pteranodons were coming out of the Niobrara chalk beds. Big ones with 25-foot wingspans and enormous head crests, and smaller, more numerous ones with modest crests. With these two different species, Chris Bennett seems to have solved the puzzle. The large pteranodons had enormous crests, longer than their bodies. The smaller pteranodons had much more modest crests, but larger pelvic openings.
The fact that they differ only in size and in the size of the cranial crest and in the pelvis made me think that they were sexes. And the fact that the small pelvis here has such a large opening makes me think that they're females.
Bennett's analysis of the bones revealed that young pteranodons grew quickly. From just a few inches inside an egg, they developed to some 20 feet across when ready to leave the nest.
The implication of this is that they would require considerable parental care. So their mothers would have to be feeding them, bringing fish and so forth in to feed them.
The development of parental care enabled Pteranodon to grow to unprecedented size, with a wingspan of more than 23 feet. But Pteranodon was dwarfed by what came later. In 1972, a pterosaur emerged from the Texas Badlands that would set the scientific community abuzz. A giant with the tongue-twisting name of Quetzalcoatlus. It was named after the Aztec deity depicted as a feathered serpent. Known from a single enormous fossilized wing bone, Quetzalcoatlus was one of the last and perhaps the greatest of the flying reptiles. It lived around 70 million years ago in the Cretaceous period, the end of the age of the dinosaurs. In the Cretaceous, the area that is now Big Bend, Texas, was a floodplain, fed by a system of rivers. The landscape was sandy and sparsely forested. Quetzalcoatlus eked out a living probing the shallows for crabs and mollusks, which it would crack with its strong, toothless beak. Quetzalcoatlus may also have lived like a vulture, scavenging meat from drowned animals. In full flight, Quetzalcoatlus would have been the size of a military aircraft with a wingspan of 39 feet and weighing up to 200 pounds. But the discovery reopened an old question. Had evolution played a trick on pterosaurs, making them too big to fly? In 1985, Paul McCready, an aeronautical engineer and a team of scientists, attempted the impossible, to build a flying model of the world's largest pterosaur. Quetzalcoatlus would be the largest flying animal of all time if it could get off the ground. McCready's prototypes, designed as gliders, launched easily. But they were not successful. McCready looked to nature. Flapping wings had to be the answer. Instead of muscles, McCready used computerized motors to simulate Quetzalcoatlus' flight. The 44-pound robotic reptile could flap and twist its wings, spread its digits, and tilt its head to compensate for wind conditions. But could technology reproduce what nature perfected? At the end of 1985, in Death Valley, California, Quetzalcoatlus made its debut. And for the first time in 65 million years, a pterosaur's shadow crossed the earth. Though McCready's model of Quetzalcoatlus was half its size and 1/4 the weight of the living pterosaur, it proved that the giant's body plan made it a powerful flyer. Pterosaurs survived for more than 150 million years throughout the age of dinosaurs. Like the dinosaurs, 65 million years ago, they vanished. Some scientists have suggested that the high winds brought on by the changing climate at the end of the Cretaceous literally blew the pterosaur into extinction. Some suppose they were simply outcompeted by birds. It may have been a matter of size.
When the pterodactyls suffered their final extinction, they were all big. I mean, really big. They were in that upper zone of mobile big critters that suffer extinction. Birds, meanwhile, include a great variety of small and medium species. So they sailed through the extinction. They survived. They were below the threshold. Pterodactyls were all above the threshold and got knocked out.
Only in the imagination of science does the pterosaur darken the skies. What we learn about these Goliaths of prehistory sheds light not upon our realm, but theirs, a dim and hazy world that we can only imagine through flights of fancy.